So welcome to lesson 2.2. We're going to talk about derivative rules now, some quick shortcuts, the idea of a tangent line, and this word nondifferentiability. Spell that, unscrabble and get lots of points. And also this idea of rate of change again. Now, just to let you know about notation here, the expression d dx means to differentiate with respect to x. It's like a verb, do it, right? Verb, do something, differentiate. The most common derivative is you want to differentiate the function y. But instead of writing it like this, d dxy, we write it as dy dx. Okay? Now, we did some of this in lesson 2.1. We had these examples, y equals to x squared plus 2. And we found that the derivative, dy dx, was 2x. We also had this function, y equals to root x, and we found that its derivative, y prime, or dy dx, right, different notation, was equal to, I believe, 1 over 2 root x. So you can double check, look back at your notes. And then we also had a third one, I think we did y equals to 2 over t, and the derivative in this case would be dy dt, because its derivative with respect to t. And we had here, I believe, negative 2 over t squared. Okay? Now, let me just change some of these forms. That square root, if I wrote it as a power, that's equal to, do you remember? X to the power of 1/2. And so if I write this derivative with that as well, that's 1/2, and then that's x to the power of 1/2, but it's in the denominator, so yes, that's a negative exponent. Good. How about this other one, 2 over t? That's the same thing as 2 times t to the negative 1 as an exponent. And the derivative here is negative 2t to the negative 2. Okay. Now, remember we did all three of these using that limit definition. But now I'm saying, hey, is there a shortcut? Looking at, let's see, this middle one here. Can you see how the x to the 1/2 becomes actually 1/2 x to the negative 1/2? Do you see what actually happened here? It looks like that power, or the exponent 1/2, got brought down to the front. And then what else? It got reduced by 1. And by the way, that gives rise to our power rule. So if I take the derivative of any power, any number of, anything in the form x to the power of n, really what I'm saying is just bring the exponent down to the front. So bring the n down to the front and reduce the exponent by 1. So bring exponent down in front, reduce by 1. Ta-da. Okay? Now, does that work for the next one here? Let's check this one in blue. Well, if I just look at the exponent part, if I bring it down, that'd be negative 1, t to the negative 2. But my coefficient in front here is negative 2, but I had a 2 in front, so I guess I just multiply that by 2. That gives rise to actually this, the scalar multiple rule. If there's a constant c in front of a function, I just have to ignore that constant and take the derivative of the function and then multiply that constant back. Okay? And then we have this constant rule. It says if any c is a constant, the derivative of c is 0. That's here, right? This 2. What's the derivative of 2? Well, there's nothing really here to connect it to it, so it's really 0. And that's what I'm saying here. The derivative of a constant is 0. And then finally, the sum rule is this one here. You see how there's two things added together or subtracted together? Well, we can just do the derivative of each of those individual two things. So the derivative of x squared is 2x. The derivative of 2 is 0. So the sum rule says just separate the derivatives to the individual pieces. Okay? And these are 4 rules that will help us help us avoid using that long limit definition to calculate these derivatives. Alright, so let's differentiate using these rules now. If I have the function x to the power of 4, yes, I just use the power rule, bring the power down to the front, and then reduce it by 1. Done. Number 2, x to the negative 2/3. Don't worry about that. So bring the exponent down to the front. and reduce it by 1. Be careful. Negative 2/3 minus 1. That's the same thing as negative 2/3 minus 3 over 3. So negative 5 over 3. Good. And then the derivative of 3, we're using the sum rule now. We're going to add the derivative of 3. The derivative of 3 is just 0, so I guess we can do that. Or just write down negative 2/3 x to the negative 5/3. Done. Now for number 3, before we actually do all this, remember, these have to be powers. Okay? Written like x to the power or something. So I'm getting scared when I see something like that. I'd rather have you rewrite it as a power. So the 5 stays the same. The coefficient here is 1/2, and now really what I'm saying is I've got the 1/2 and I got this 1 over t cubed. How do I write 1 over t cubed? As a power? That's t to the power of, negative 3. Great. Once you've done that, let's go ahead now and take the derivative. See my notation, h prime of t now. So the derivative of 5 is, of course, 0. This is a constant, so we can just ignore it. And then now let's take the derivative of t to the negative 3. That's negative 3, t to the negative 4. And then we'll just multiply the constant back in. So that's 3 over 2 times t to the negative 4. Okay. All right, and number 4, same idea, but we have this bracket cubed. I'm going to ask you to expand it first, so let's just rewrite this as 5 over 8x cubed, or better yet, how about 5/8 x to the negative 3? And since now we've got it in nice power format, we can now take its derivative, f prime of x. That constant in front we'll ignore. We'll take the x to the negative 3 and apply the power rule, negative 3x to the negative 4, and then we'll just combine the coefficients together. There you go. Isn't this much easier than doing the long form of the definition of derivative? So memorize these. Good. Now, there are something called higher order derivatives. Yes, so since the derivative of a function is just another function, we can actually repeat that process and find the derivative of a derivative. The result, of course, is still another function, which again could be differentiated, so we can actually do it over and over again, and that's why we call these higher order derivatives. We've looked at the notation for the first derivative. We're good with that. The second derivative, instead of y prime, is y double prime. Instead of f prime of x, it's f double prime of x. And then instead of dy dx, it's d2y over dx2, or dx squared. Or if they're like this formula, or this notation, I should say, d squared over dx squared f of x. I actually don't like these ones. I think this was really confusing. This is decent. I prefer actually one of these ones here. That's my preference. This one, okay. But nonetheless, the third derivative, 3 dashes, d cubed, or d3i over dx cubed, and 4. We don't do any dashes anymore. We just write the number 4 in a bracket. Okay? All right, so example number 5. Whoa, some messy things. Can you find the first derivative, and not only find it, but evaluate it at 1, and then do the same thing with the second derivative, f double prime, and evaluate that at negative 8. So I always like to change the function into a power. I have 1/2 as a constant. This is x to the power of negative 2/3. Knowing that, I can take the derivative now, ignore the constant in front, negative 2/3 x to the negative 5/3, simplify this, and voila, I'm done. Oops, not 5/8, 5/3. If I want to now evaluate and calculate f prime of 1, just plug in 1. Negative 1/3. Okay. Good. The second derivative is just, of course, the derivative of the first derivative. So I'm going to take this simplified form and take its derivative. So 1/3 is a constant. Ignore it. Bring down the exponent. Reduce it by 1. And then now if I want to find the second derivative at negative 8, yes, I got to plug this in. This does not look fun, but nonetheless, I'll just leave it like this. And this is my exact answer, okay? You can punch this into a calculator, get 3 decimals, that's fine too. Alright? Okay, so lots of skills, mechanics that I'm doing with you. Hopefully we can now apply it to something. So let's turn the page. Remember this idea of an equation of a tangent line? Yeah, well, since the derivative of a function actually gives us the slope formula, we can actually use the derivative to help us find equations of tangent lines. Because to find the equation of a line, we need a point and that's right, a slope. And what is a slope? Yeah, it's a derivative. So sometimes you also want to find the line that's perpendicular, right? And in calculus, we call that a normal line. So perpendicular, normal, same idea. And we learned in Unit 0 that the perpendicular slope is just negative reciprocal, or negative 1 over the slope of the tangent line. All right? So let's go ahead and try this now. Find the equation of a line tangent to this graph at a particular point. Well, what did I say we need? We need the slope and we need the point. We got the point. Cool. We need to find the slope. How do we find the slope? Yeah, it's the derivative. So let's go ahead and take the derivative. Let's take the derivative. So here we go. What do we have here? 4x to the power 5. That's, oops. Getting ahead of myself here. 5x to the power 4 minus 3. The derivative of x squared is 2x. The derivative of 5 is 0. If you want to simplify this to make it nicer, by all means, please do. Ta-da! But I want to find what? The derivative at a specific point. What specific point am I asking this for? X equals to 1, so I better plug in 1. That's correct. 14. And so knowing that, I can use my point-slope form for the equation of the tangent line. That's y sub 2 minus y sub 1, or, sorry, I think we did it this way. Y minus y sub 1, yeah, equals to m bracket x minus x sub 1. You can use slope y-intercept form if you want to. I don't really care. I didn't say you had to do one way or the other. I just think this one's much easier. Okay. Done. There's the equation of tangent line. Oh, what about this normal line? Well, remember the normal line? So m normal is just the reciprocal. Well, it used to be 14, so not just the reciprocal, my fault. Negative reciprocal. So 1 over negative 14 here. And same idea now. So y minus 6, that's just negative 1 over 14, x minus 1. There's my normal line equation. Okay. All right, another concept here, nondifferentiability. That's when a derivative does not exist. Remember that derivative is really a limit, and limits cannot exist, so therefore, of course, derivatives might not exist. Where might they not exist? Here are a few samples of how a derivative does not exist at the point x equals 1. Whole, right? Don't know what it is from the left, don't know what it is from the right. A jump, problem there too. Vertical asymptotes, undefined. A sharp turn, because the derivative from the left does not equal to the derivative from the right. Hey, I can use this kind of notation. F prime from the left of a function does not equal to f prime from the right of a function. And then a vertical tangent, once again, problems because the slope is undefined for a vertical line. So these 5 characteristics destroy, what a hard word, destroy differentiability. The first 3 are discontinuities. There are breaks in the graph. These last 2 are not breaks, but they're sharp turns or vertical tangents. Okay. And a note here, please. If a function is not continuous, it is definitely not differentiable. Those are the first 3 examples. All right, not continuous, not differentiable at that point. But a function can be continuous and still not be differentiable. Those are examples 4 and 5, right? The absolute value graph, sharp turn, or vertical tangent. So make sure you understand that too. Knowing those things, let's turn to the next page. And I'm going to ask you to please look at these examples and see if you can find the x values where the function is not differentiable. Okay, and then tell me a reason as well. Okay. Ooh, number 8. The absolute value of x. Oh yeah, if you graph that out, what do you see at 0? It's not differentiable at 0 because there is a sharp turn. Good. Number 9, interesting. X squared. That's this parabola. X. That's okay. It's continuous, isn't it? Oh, but why is it not differentiable at, I think, 0? Yeah, because here we have, once again, also a sharp turn. Now, another way to see this without looking at the graph is to actually find the derivative of the piecewise function. 2x, of course, if x is less than 0. 1 if x is bigger than 0. And then at 0, evaluate, right? F prime of 0 from the left will be 2 times 0, which is 0. F prime of 0 from the right would be the value 1. They're not the same, therefore the limit doesn't exist. Problem. Okay. Now for this one, you can think, let me do the derivative. Yeah, 2x. Yeah, 2x. Yeah, derivative from the left. 0. Derivative from the right. 0. So there is no problems anywhere. But the problem with that is you have to look at the function itself. Y equals x squared. That's this. Y equals x squared plus 1. Uh-oh. I see a jump. So even though this derivative here is the same, be careful. Look at the function itself too. The function itself is not continuous. So wherever it's not continuous, it's definitely not differentiable. Not continuous. Why? Because it's a jump, and therefore not differentiable. End of story. 11, you might think, where's my issues? Well, yeah, definitely. X equals to 1, that's a vertical asymptote. Problem there. Not continuous. And don't forget, don't forget also here, the x and the x, that simplifies. That means that must have been a whole. Therefore, x equals 0 is also a place where it's not differentiable. And once again, not continuous. For 12, interestingly enough, I can make this x to the 1/3. So if I take the derivative, notice what I get, 1/3 x to the negative 2/3. And if I were to figure out or rewrite this as a root, that's what I get here. Uh-oh, denominator, be careful. I have to make sure the denominator cannot be equal to 0. Uh-oh, where is it equal to 0? Yeah, at 0. That's a problem. And if you think about what this looks like, 1 over 0 is undefined. Remember, this is the derivative, so the derivative is undefined. So we have here a vertical tangent line. And you can graph this out and see it too. You'll see that the graph, I think, goes something like this. And at 0, we have a problem. Okay? So, make sure you understand those ideas before we move on to the next thing. We're going to come back to this idea of rate of change again. So remember, average rate of change is just the slope of the secant line, the stuff we learned in pre-calculus. My rubber boat song, remember? Slope equals y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. If you missed out, go back and watch Unit 0. But now, using differentiation, we can also find the instantaneous rate of change. That's the beautiful part of calculus. I don't have to wait for a start and stop. I can actually press pause on this video that I'm playing and see what's happening at that moment when I press pause. This, of course, is the slope at a single point, and therefore you use calculus. We use the terminology IROC for instantaneous rate of change. Single point means derivative. Woohoo! So, find the average rate of change for number 13. Once again, that's the slope formula. So that's f of 30 minus f of 10 all over 30 minus 10. I should label this as average rate of change. We would calculate these things. 30 cubed plus 20 times 30 minus 10 cubed plus 2 times 10. Be careful to put a bigger bracket because this minus sign applies to both. This is over 20. What is this equal to? Big numbers, big numbers, big numbers. I think it's 27,060. This is what, 10,000. Oh no, 1,020. think that just becomes 1,302. Trust me? Yeah, trust me. Okay, so really what I said is, okay, the average rate of change between 10 and 30, 1,302. But that's not what I want. I want to find the instantaneous rate of change now when it's 20. Or not 20, but 10. So the instantaneous rate of change, once again, IROC, is defined as the derivative of the slope of the tangent line. So I'll quickly find the derivative of the function. What's the derivative of x cubed again? 3x squared, yes. And then we're going to use the sum. And then the derivative of 2x is, that's right, 2. And then what about me plugging in 10? 100 times 3 is 300 plus 2 is 302. And this is the instantaneous rate of change at x equals 10. Alright, lots of concepts in this one here. You need to do lots of practice, please. Okay? Do the practice. Do it well before we move on, or it's going to be trouble ahead.